Today, we're going to continue looking at double integrals. Remember that most of the work we've been looking at doing so far has been setting up a double integral, describing a region so that the integral will understand it. What we're doing in integration is adding up a bunch of values for the function, just evaluating the function at a bunch of places and adding up the results. When we had a function of a single variable, it was easy to describe the values that we're plugging in. Start at A, end at B, that was it. But when we have a function of two variables, we're plugging in sets x and sets of coordinates, plugging in an x, plugging in a y. So we're picking all the values over a region in the xy plane. Intervals always have a boring shape, but regions in the xy plane can have all kinds of funky shapes. So we came up with this plan. We'll just say what's x between, what's y between. That's how we'll describe all the values that we plug into the function, then add up. So let's take a look at this region. Here we have a region described already in the integral, the double integral. So let's take a look at what this region looks like. So we've set this up as a dy dx. So since we started off with a dy, that means this first integral, or the inside integral, is y equals x over 3 to y equals 2. It's also obvious that the dy goes first because our first integral has an x in it. This can only be an integral of upcoming variables. So because the dy is listed first, that means the x over 3 and the 2 are y's. The dx is next. And since the dx is next, that means we're integrating x between 0 and 6. Normally, we wouldn't write the x equals and the y equals, but we're new at this double integral business, so we're just going to remind ourselves. It's like when we were first learning algebra. If we had 5x minus 4x, we would write the 1x to remind ourselves that when we just write x, we mean 1x. So let's draw this region. We know that we want all the x values between 0 and 6. So I know I'm going to have x equals 0 on my left and x equals 6. So there are our vertical sides of the box that our region is going to fit into. The bottom of the box of the region is going to be x over 3, and the top of the region is going to be a nice constant y equals 2. So I'm going to draw that in there. And then, so now I'm just going to draw the graph between x equals 0 and x equals 6. X equals 6, we're going to draw y equals x over 3. So fortunately, that ends when x is 6 and y is 2. So y equals x over 3 goes from 0, 0 to 6, 2. So there's the bottom. Here's y equals 2 at the top. Here's x equals 0 on the left. And here's x equals 6 on the right. So here's our region up in here. Any questions? Yesterday, I would have drawn the region and had you write the double integral. Today, I want to write the double integral and have you draw the region because we have to know things forwards and backwards. Now, let's change the order of integration and write a new double integral. So now let's write a double integral. Instead of dy dx, let's write this integral dx dy. So we're going to write a new double integral. We're going to integrate. We actually have a function today. Since I've actually written a function, you could probably guess that we're going to be evaluating a double integral today. But I want to change the order and go dx first, and then dy second. All right. When we're writing a double integral, always do the second thing first. Figure out what the constants are at the end. So since I'm writing a dx dy, the dy is going to be our last integral, and that one has to be between constants. So I'm not going to use y equals x over 3 as the bottom because this last integral has to be constants. The top is still 2, but the bottom, the lowest y value as a constant that we see is y equals 0. So from the constant standpoint, we're integrating from 0 to 2. Then we move in and think about left to right. We pick a particular value of y, find the lowest x and the highest x. So here is where we're going to get the shape. So because we're doing dy as the outside integral, the second integral, that one has to be constants. So instead of using y equals x over 3 as the bottom, y equals 0 is the lowest x value, y equals 2 is the highest x value. So now I pick a generic value of y and find the lowest x and the highest x. So here, x starts off at 0. And I can't use y equals x over 3. I've got to turn that around for x. So I'm going to integrate to x equals 3y. So in this integral, the bottom to top is the constant parts. Left to right is where we're going to get the variable stuff. So here's the integral written in the other direction. Any questions? Now, you've noticed that I've written a function instead of just writing a generic f of x and y. So next, let's evaluate the double integral. So now let's move on to evaluate the double integral. Here's where we're going to run into a problem. This particular double integral comes pre-programmed with a problem for us to run into. If we look at this first double integral, where we're integrating x from 0 to 6, and then y from x over 3 to 2, if we look at this integral, to evaluate this integral, the first thing we would look at is integrating with respect to y. The problem is we have the square root of y cubed plus 1. We don't have a nice antiderivative of y cubed, the square root of y cubed plus 1. We don't have any anything on the outside to support a substitution. We're a little bit stuck here. So the problem that we've run into is that we can't integrate dy. So this first integral here we don't have what I used to call, for those of you who are in my Calc 2 class, a nice antiderivative, where we can just apply some rules to it and come up with a finite combination of elementary functions. I started saying nice because finite combination of elementary functions is a little bit of a mouthful. We don't have an antiderivative that's a finite combination of elementary functions, because it's the square, we'd have to integrate the square root of y cubed plus 1. If it was just y cubed plus 1, no problem. If it was just the square root of y cubed, no problem. But it's the square root of y cubed plus 1. That would be no problem. Square root of y cubed, it's just y to the 3 halves. But then we're like all plus 1. What a bunch of trouble that plus 1 makes. Fortunately, we had just spent the previous problem, in the previous part of this problem, rewriting the integral in the other order. So fortunately for our heroes, we had just spent some time rewriting this as the integral from 0 to 2 and from 0 to 3y, x times the square root of y cubed plus 1 dx dy. Now our first integral is an x integral, and the square root of y cubed plus 1 is constant. So now our first integral in here that's something we can integrate, because the variable part is just the x. The square root of y cubed plus 1, that's constant with respect to x. In the previous double integral, the square root of y cubed plus 1 was the variable part that we had to integrate. X was the constant with respect to y. But now in this formulation, we're integrating with respect to x, so that's the one to use. So you'll notice that I haven't talked about how to integrate functions with respect to x. But we have talked about how to differentiate functions when there's more than one variable running around. And so we're just going to do that in the other direction. So this is the one that we're going to use. This one, we're just going to say, well, they're both equal, so we'll do the second one because it's easier. So we're going to integrate from 0 to 2. Now I need to find the antiderivative of x times the square root of y cubed plus 1 with respect to x. So the square root of y cubed plus 1 is all constant. I'm just integrating x. So I get a 1/2 x squared. And the square root of y cubed plus 1 is all constants. So here's our antiderivative. And then we evaluate from 0 to 3y. So we evaluate from 0 to 3y. This is all still inside the integral dy. Now, at this point, you should notice that eventually we're going to have to integrate this dy. So I hope you got some kind of plan up your sleeve problem, because the bill is going to come due on this square root of y cubed plus 1. But that's okay. We're about to plug the 3y in, and looking ahead, see where the 3y is going, and then look at the setup we'll have. We'll have a y cubed in here, a y squared out here, and we're going to get a nice substitution problem. That's because this problem is super contrived to do exactly what we want it to do. All right, so now let's plug in the 3y and plug in the 0 and evaluate. So we have a 1/2 3y squared times the square root of y cubed plus 1 minus 1/2 0 squared times the square root of y cubed plus 1. This is all still inside the integral dy. So we're evaluating this integral. Here's what we got for that integral. We're still evaluating that integral, the x integral. We're just treating y as a constant. So fortunately for our heroes, this whole term drops out. And so now we have just a function of y, and we're integrating from 0 to 2. So now we're integrating from 0 to 2. We're going to have 3 squared is 9/2 y squared times the square root of y cubed plus 1 dy. And now our dy integral is up next, but it's a substitution problem. So before, when we just had the square root of y cubed plus 1, we don't have a nice antiderivative, can't proceed. But if we change the order of the integration and integrate with respect to x work, because this problem was custom built for this exact purpose, now we can integrate it. This is one of those problems that you do so much of, you start to think that this just must happen all the time. It's like when you were learning to factor polynomials. Like most polynomials are factorable because almost all the polynomials I run into, they're factorable. And it gives you this false view of the world. It's like you're in an information silo. In 2021, we actually have words for that kind of stuff. Or we've always had the words. They're just in more common use. So now we can integrate this function. We're going to say w is y cubed plus 1, so that the dw is a 3y squared. So I'm going to go through the details because it might have been a while since we've done this. Let's turn the page and go through the details. Copy and paste. So now we can evaluate with substitution. We didn't have this option before. We can set w to be y cubed plus 1 and dw will be 3y squared dy. We didn't have this option before because we didn't have the y squared on the outside. We just had the x. But once we integrated with respect to x, we ended up with an x squared. We plugged in a y. All right. So the y squared dy will all be a 1/3 dw. So the parts that we have. I'm going to pull out the 9/2. I'm going to factor out the 1/3 because this is all constant stuff. We're still integrating y from 0 to 2. Y squared dy is all going to be 1/3 dw. The y cubed plus 1 is going to be w. So we're just integrating the square roots of w dw. Any questions? All right. So the integral of the square root of w, that's a w to the 1/2 power. So we're going to have a 2/3 w to the 3/2. So I've got this 9/2. No, I wrote it already. 9/2, and then I've got the 1/3. Then I've got to integrate the square root of w. And this is w to the 1/2 power. So we'll have a 2/3 w to the 3/2. Oh, and I've already made a mistake. We're not integrating from 0 to 2. That's not where we're integrating anymore, because those are y values. If y equals 0, then w is 0 cubed plus 1, or 1. So we should integrate from 1. And when y is equal to 2, w is equal to 2 cubed plus 1, which is 8, 9. So we're not integrating from 0 to 2. That's what we were integrating in y. We're integrating w now. So we'll integrate from 1 to 9. That way we don't have to go back to y. Let's just integrate from 1 to 9. Let's also take care of all this business. So 9, 9 to, oh, that all cancels out. How handy. So I just get 9 to the 3/2 minus 1 to the 3/2. 26. So it's super convenient that the stuff that we plugged in after the first integral was easy to do. And the stuff that we plugged into it set us up nicely for a substitution problem. It was very convenient, a little bit contrived. If only we had a wheelbarrow. Any questions? So a few new things today. We practiced sketching a region using a double integral, taking the description of a double integral and drawing the region. We rewrote the order of integration, and then we actually integrated a double integral. And integrating a double integral is just like an iterated integral, excuse me, is just like when we were finding partial derivatives. We treat there's one variable that's in play, then the other variable is considered to be constant. We integrated with respect to x so that the square root of y cubed plus 1, that was all just a constant. If we had adjusted it a little bit and it was the square root of y cubed plus x, now we got a problem because now we have a product that we'll have to find some other way to integrate. Y cubed is still constant, but that change might not make our second integral work out so nicely. I usually refer to these as wheelbarrow problems, and for the most part, no one gets the reference anymore, but that's okay. This means I'm older than y'all. Any questions, comments, snide remarks? It's also like a just classic video game design. You switch the order of integration and you get the thing that you need right before you need it. It's dangerous to go alone. Here, take this. So like just before he left on this quest, I was like, oh, hey, you could switch the order of integration. And then next boss fight, what did you need? Switching the order of integration. And it worked out perfectly. Any questions, comments, deep thoughts? All right, so that there are hundreds of problems for you to practice on in section 16 point double integrals. 16.2 is the iterated integrals one. That's got a lot of regions for you to sketch. That's got a lot of double integrals for you to write. And that's got some integrals where you have to change the order just to do the integral. So sometimes you have to evaluate the integral. Sometimes we're focused on just writing the double integral, setting up the problem. All right, I just wanted that one problem today. I wanted to take a region, sketch it, and then change the order of integration. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.